So, in this lecture I will discuss about the second mode of corrosion, that is aqueous corrosion, particularly that is galvanic corrosion. So, galvanic corrosion is a form of corrosion which usually occurs when two dissimilar metallic materials are electrically connected and they are placed in an aqueous media or electrolyte. So, usually the potential difference existing between the two dissimilar metals is the driving force for the corrosion to occur. So, this is the case for copper and steel which is actually soldered. So, you will see that there is extensive corrosion at the steel surface of this particular steel part of the pipeline combinations as compared to that of copper. This is because of the fact that steel is basically more prone to corrosion or active as compared to that of copper. So, when two metals are actually joined together, you see that the steel basically goes on corroding as there is a flow of electron or evolution of electron, that electron actually saves the copper to a large extent. So, like that you will find that steel goes on corroding and that corrosion proceeds from the junction point towards the other end of the particular pipeline. So, these galvanic corrosion can be a dangerous form of corrosion which basically starts at the interface and then proceeds to a large extent towards the other side of the component, and it is naturally a kind of localized form of corrosion. And when it occurs in many cases not only in dissimilar combinations, but when the metal which is having dissimilar phases, they are also depending on the corrosion probability or EMF of the individual phases, you will find that corrosion there may be a micro galvanic cell formation, and as a result of which galvanic corrosion proceeds. So, usually metals and alloys if you just talk about general corrosion or atmospheric corrosion in normal environment, they are basically standard EMF series plays very important role to choose the materials, but whenever you talk about the application of metals and alloys in quantitative application of metals and alloys in normal environment, actual environment, there the series which is applied is galvanic series. So, that galvanic series is nothing but it gives you information about the relative corrosion potential of that different metals in that different in the metals as well as alloys in different environment, and that galvanic series plays a very important role to choose the materials for galvanic combinations. So, basically you have to be careful to choose the materials for that to prevent the galvanic corrosion. You must choose the materials which are very close in the galvanic series for the prevention of galvanic corrosion. So, this is typical example of the galvanic series where like different steels as well 18-8 stainless steel which is passive and noble naturally, and then nickel and then copper, tin, brass, 18-8 again it is MS, aluminum, zinc, magnesium. They are actually they are sequentially arranged from the noble end to the active end in marine water environment. So, as I mentioned you that the driving force for this galvanic corrosion is the potential difference, the EMF difference of the two metal when they are joined together in aqueous environment. So, this is the case for the zinc and copper. Whenever you immerse it in typical hydrochloric acid solution, you will find that, and if you connect them properly, you will find that the zinc corrodes and at the expense of copper. So, copper is actually protected, but zinc goes on corroding to a large extent. So, this is typical galvanic cell, and you will find that the galvanic cell formation usually occurs or galvanic corrosion usually is observed not only when you just connect two dissimilar materials or two dissimilar metal together, but also it can occur by different other reasons as well. For example, if any, as I mentioned you, in any microstructure, if you have different phases and different phases having different corrosion potential, you will find that there will be micro galvanic cell formation between two different phases, and as a result of which problem starts at the interface and it proceeds thereafter. When there is difference in concentration of the metallic ion, then also the galvanic cell might form. Difference in concentration of the oxygen, there also there may be galvanic cell formation. Difference in residual stress level. So, for example, in one case you just partially cooled work one metal, and other part is actually recrystallized or annealed, you will find that due to residual stress difference, the cold work site is corroded to a large extent as compared to that of annealed site. Similarly, difference in temperature, if there is difference in temperature, usually high temperature regime acts as a anode as compared to that of low temperature regime, as a result of which you will find that more corrosion attack is there in the high temperature region. So, like the different examples are also shown here. For example, different phases even of the same metal can form galvanic couple at the microstructure level. Like in steel, cementite is noble as compared to ferrite. So, if you just take eutectoid steel of plain carbon steel of eutectoid composition, you will find that there will be due to galvanic cell formation and also because of the galvanic corrosion, the ferrite part degrades or corroded to a large extent as compared to that of cementite part. So, it may be formed by because of the concentration difference of metal ion. In an electrolyte, you call it concentration cell, where metal ion deficit part acts as anode and metal ion excess part acts as cathode. You can also form that microgalvanic cell when there is a oxygen deficit regime or oxygen enriched regime. For example, in case of previous corrosion, you will find that the differential aeration cell formation is there because of oxygen concentration difference, which basically is nothing but the kind of galvanic attack. So, initiation starts because of the galvanic corrosion and then it proceeds thereafter to a large extent because of the autocatalytic reaction. Then galvanic shell may form because of difference in residual stress. As I mentioned you, that stressed region is more acts as anode as compared to that of stress free region. And galvanic cell may form due to difference in temperature in the same metal, like high temperature region. High temperature region is more active, usually acts as anode as compared to that of low temperature region. So, if you take a component having different temperature in different region, you will find that different temperature region basically corrodes to a different extent. So, you have to be very much careful, and in addition to that there is also the galvanic cell formation. So, as I mentioned you that galvanic series actually plays a very important role and also acts as a guideline for choice of material for galvanic coupling. So, whenever you have the necessity for application of two different metals or coupling of two different metals, you just choose them which are more close in the galvanic series. Like for example, the case for copper, nickel and silver solder. For you, if you are interested to just couple copper with copper nickel alloy, that is very much acceptable. Copper can be coupled with brass as well. Then tin can be coupled with brass, there will be very less galvanic attack. But if you go on coupling steel with aluminum, bronze or steel with nickel, you will find that lot of galvanic attack will be there or lot of corrosion will be there because of the galvanic corrosion. Similarly, if you just choose zinc and titanium or zinc and stainless steel, you will find that there will be lot of galvanic attack. So, whenever you just go on choosing material combinations, this galvanic series plays a very important role and acts as a guideline for the choice of the materials combination for a specific purpose. Now, the factors which influence the galvanic behavior, they are ample. For example, the potential difference between metals and alloys. So, how they are basically placed in the galvanic series. Second part which is very important is that the kind of environment the component is exposed to, because depending on the environment again the position of different metal or chemical reactiveness of different metal changes. So, the environment which is actually the surface environment of the component couple, that also plays a very important role. Polarization behavior of the metals and alloys, geometrical relationship of the component metal or alloys, and naturally temperature differences, stress differences, microstructures, these all factors play a very important role, play important roles actually to determine the galvanic corrosion behavior of the materials combinations. So, this is there are few examples of the galvanic corrosion. For example, this is the schematic showing break in the Mill scale, actually there is a breakage of the Mill scale, and because of that naturally the fresh surface is exposed and one surface is actually it is still there. You will find the scale is still there, you will find that there is galvanic cell formation, and as a result of which the in the broken surface or exposed surface, the rate of attack is more than that of the unbroken part where scale is remaining. Similarly, this is the case for galvanic corrosion of aluminum shielding in buried telephone cable coupled to buried copper plates. So, we will find that at the particular that aluminum copper is highly stable as compared to the aluminum. We will find that due to galvanic attack the aluminum is basically destroyed to a large extent. So, current path in the electrolyte between two metals, for example, if you have that anodic metal and then cathodic metal. So, you will find that naturally the problem starts at the interface. So, that anodic side basically corrodes to a large extent, and by that process it protects the surface of the cathodic metal. So, if you just go on measuring the potential of the anode and cathode, you will find that E anode is naturally quite less, this is active in nature, and E cathode is very high. So, you will find that from the interface the corrosion rate also changes. So, near to the interface the corrosion rate actually is quite large, and as you go on proceeding towards the anodic side, naturally you will find that E corrosion is near to that of metal of that E corrosion of the anode. So, naturally you will see that usually that the interface plays a very important role, and every problem starts from the interface. This is the galvanic corrosion of aluminum and copper coupling, as I mentioned you. Again galvanic corrosion of painted steel body, steel auto body. So, you will find that there is by some way, by erosion corrosion or by the typically the exposure of this particular painted surface to environment, if there is breakage of the or if there is damage of the paint layer, you will find that there will be galvanic attack, and this particular paint layer basically cannot save the underlying metal because of the cathodic protection, because paint is usually noble in nature. So, you will see that underlying metal actually corrodes to a large extent, and rate of corrosion of the underlying metal is much higher than that of exposed part normally, which is not painted. Similarly, galvanic corrosion of steel pipe at brass fitting in humid marine environment, you will find that where underneath that of kind of brass this thing, there is a lot of corrosion in the steel, and naturally you will find that this brass is nobler compared to that of steel. So, you will find that steel plate is or steel part is that damaged to a large extent as compared to that of the part where there is no connection actually, or there is no coupling. This is the case for carbon steel stainless steel combinations. It also depends on, you will find that carbon steel that this particular galvanic corrosion current density is much higher than that of stainless steel, which is basically non corroding in nature, and it also depends on the resistivity of the environment solution, particularly in water environment where resistivity is quite low. Here you will find that corrosion rate is much higher, current density in terms of galvanic current density as compared to that of the case where resistivity is very high. So, resistivity of water, naturally ionic conductivity plays a very important role, ionic conductivity of the electrolyte plays a very important role. Higher is the ionic conductivity, naturally higher will be the rate of corrosion attack. So, this is again the combinations for iron and copper. So, you will find that if you go on insulating the part, naturally you can minimize the tendency of the attack of the typical anodic part of the combinations of the couple. This is the case for thermogalvanic corrosion, where you find that hot part actually acts as anode as compared to that of cold part, and problem starts at the interface. Now, if you quickly go through the way by which you can combat the galvanic corrosion. So, usually the way or that techniques normally applied for prevention of general corrosion, some of the techniques are also applied or can be applied for the prevention of galvanic corrosion. They are like cathodic protection, application of inhibitors in the environment, application of coatings. So, these are very standard way of protecting the surface for any kind of corrosion, but apart from that you can also choose the proper material combinations which are very close to the galvanic series. You can apply insulation in between the dissimilar materials, and also another very important way of prevention of galvanic corrosion is by avoiding the unfavorable area effect. So, usually corrosion, whenever you talk about corrosion rate, current density is very important. So, if you have a very large area of contact of the anode as compared to that of cathode, you will find that current density will be much lower. So, naturally, as a result of which you will find that degree of effectiveness or degree of corrosion will be reduced in the anode. So, if you have a very large area cathode to cathode ratio, you can reduce the probability or you can reduce the overall corrosion rate of the anode as compared to that of other way where you have very low anode to cathode ratio, very small area anode to cathode area ratio. So, you have to avoid the unfavorable area effect actually. So, you have to, whenever you have the possibility of galvanic coupling, you choose the anode which is having much higher area than that of the cathode, which is beneficial because it will reduce the current density and as a result of which corrosion rate of the anode. So, now third type of corrosion is crevice corrosion. So, crevice corrosion is a kind of corrosion which occurs at the shielded areas that contain a small volume of the aqueous solution. So, usually when there is chloride in the environment, it is basically aggravated, but it is not necessary to have the chloride in the environment. So, as I mentioned you that that galvanic corrosion, basically the crevice corrosion, the processes or corrosion initiation mechanism is by galvanic attack, because whenever there is like shielded area, you will find that in the inside the shielded area the air concentration is much higher than that of outside shielded area. So, as a result of which there is differential aeration cell formation, and because of differential aeration cell formation, you will find that there will be galvanic attack at the interface between the high air region as well as low air concentration region. So, because of that again galvanic attack, the corrosion starts, and as soon as it starts you will find that in the crevice region where there is electrolyte solution, but air concentration is not enough, you will find that there is no more the air which is available is not adequate for the passive layer formation, and as a result of which you will find that corrosion rate of the inner layer is much higher and it go on proceeding to a large extent as compared to that of outer layer, particularly because of the differential aeration cell formation. And this particular case is further aggravated if there is chloride in the environment, because chloride they basically bleaches the oxide film. Not only that, chloride actually increases the corrosion rate to a large extent. So, presence of chloride is not really is dangerous, where crevice attack is the main form of corrosion in engineering practice. So, you will find that this crevice corrosion is observed in different, not only in that shielded area, but also in any area where there is for example, where you have washer and that is loosely shielded actually. So, there also you will find that typical crevice corrosion problem is existing. So, it occurs with bolted parts and threads when submerged in electrolyte. The crevice creates a small anode and the remainder of the sample it is being a large. So, here another problem is also there, not only the differential aeration cell formation, but also the unfavorable area ratio is also existing, because in the crevice region the area is much lower than that of the outside region. So, because of the very low anode to cathode ratio, you will find that, or very small anode to cathode ratio, the corrosion rate inside the crevice region is much higher than that of outer part. So, you have to be very much careful and design the component combinations properly, so that you can combat the possibility of the crevice attack. This is the example of crevice corrosion at a metal to metal crevice site formed between the components of type 304 stainless steel fastener in seawater. So, you will find that lot of crevice corrosion is there at the in the fastener. Again, crevice corrosion at non-metallic gasket site on an alloy 825 seawater heat exchanger. So, in the gasket pipe you will find that because of the presence of gasket, usually that part is actually there. Crevice corrosion creates lot of trouble and it damages the surface to a large extent. Then crevice related corrosion for different alloys in natural seawater, again you will find that lot of corrosion is there at the crevice site as compared to that of our surrounding region. So, if you just quickly go through the different factors or parameters which influence the crevice attack of a component, these are amples, for example, the type of crevice, whether it is metal to metal combinations or non metal to metal combinations, the gap, degree of tightness, then crevice depth, then exterior to interior surface area ratio. Because as I mentioned you that these all factors play very important role, because if you see carefully the factors, you will find that like type of crevice, whether it is metal to metal or non metal to metal. If it is metal to metal, they are quite close to this galvanic series. On the other hand, if it is non metal to metal, they are widely apart in the galvanic series. So, you will find that probability of crevice attack will be more when there is non metal to metal attack as compared to that of metal to metal attack. Again, crevice gap is very important, because lower is the gap, smaller will be the electrolyte, and larger is the gap, naturally higher will be the electrolyte in the crevice side. So, accordingly you will find that attack rate will also vary. Crevice depth is also very important. So, where you will find that as you go on increasing with depth, or if you go on changing depth, you will find that attack rate will be usually more actually, because on the surface the attack rate is much lower, because it is exposed to the environment. So, there is possibility of the oxide layer formation, and as you go on decreasing, as you go on proceeding towards the depth, you will find that there will be more less oxygen supply or less air supply, as a result of which you will find that there will be the more tendency for the crevice corrosion. Then exterior to interior surface area ratio, it basically controls the this is the basic principle of combating the galvanic corrosion. Higher is the ratio of the anode to cathode, naturally lower will be the crevice attack, but lower is the anode to cathode ratio or smaller is the anode to cathode ratio, higher will be the crevice attack. Then if you talk about environment, then whether it is how much is the oxygen content in the environment, how much is the pH in the environment, then chloride level, temperature, agitation, these all play very important role. So, mass transport migrations, whether there is any kind of stirring action in the environment, diffusion and convection, whether any flow is there, flow is whether lamellar flow or convective dominated flow. So, whether there is any biological influence, sometimes the microbiological species, if they are in the environment, they basically get accumulated on the surface and it acts as the site for the crevice corrosion initiation. So, as if you do not clean it properly, you will find that after a while there will be lot of crevice attack, and you have to be very much careful to repair the part, otherwise there will be severe damage of the component. If you talk about electrochemical reactions, they are metal dissolution, oxygen reduction and hydrogen evolution. So, these are very important, and also metallurgical phenomena or metallurgical parameters which are important. They are nothing but the elements or maybe the components, that ingredients in the alloy, whether any impurities are there, whether there are different phases in the particular alloy, then what is the passive film characteristics, whether passive film is stable or non-stable. For example, if you take the case for 304 stainless steel, you will find that it is more prone to crevice attack as compared to that of 316L stainless steel or 316 variety of stainless steel, which contains a little bit of molybdenum. So, when molybdenum is there in that particular alloy, you will find that film is highly stable as compared to that of chromic oxide film, which basically protects the surface. So, when that molybdenum is there, it forms a complex oxide which is stable in that particular crevice environment or chloride containing environment, which is more stable, and basically it reduces the probability of crevice corrosion. So, one of the important form of crevice corrosion is filiform corrosion, which usually is observed in the painted surface. So, what happens is that in the painted surface there is always very small nano level perforations or porosities, micro level porosities to nano level porosities. So, through the porosities there is always that water molecule absorption, and when the water molecule get absorbed on the surface, there is iron oxide formation, ferric oxide and also ferric hydroxide formation, and you will find that there is always concentration in the, whenever if you see the this particular formation probability or formation rate in different regions, you will find that it is higher at some region, some of the part of the region, it is not uniform rather, because wherever there is perforation, very small porosity is there, through there only, through that porous region only there is migration of the water molecule, and then there is formation of iron hydroxide. So, whenever there is hydroxide formation, there actually there will be much more moisture absorption. So, there is always a differential aeration cell formation, and also there are different phase formation like microgalvanic cell formation, because hydrides are more stable as compared to that of iron which is there. So, as a result of which, because of the galvanic cell formation and moisture absorption, this particular reaction proceeds from the from one side to other. So, initially the attack starts at some region where there are small perforations or damage or porosities on the paint surface, but as soon as it forms, the one end gets opened, and through that end there is water molecule migration, and then there is differential aeration cell formation, and subsequently corrosion of the other part of the metal, and this particular thing proceeds in a tubular fashion, and you call it as filiform corrosion. So, when you look at the surface, you will find that it basically the filiform filiform corrosion, basically the appearance of the filiform formation is like in a tubular fashion zigzag zone on the surface. This usually is observed in aluminum, magnesium, iron, these all surfaces whose hydroxides are very much prone to get hydrated or prone to absorb moisture, and which is very much prone to form the which are very much prone to corrode in aqueous environment. So, another type of important corrosion is the pitting corrosion usually. So, that I will discuss in the next class, but before the beginning of the next talk, I must say that crevice corrosion, galvanic corrosion, these are very important kind of corrosion, because they are basically localized in nature, and whenever you talk about this kind of corrosion, you have to be very much careful again to choose the proper material. If you talk about the prevention of the crevice attack, then you have to be careful in cleaning the surface at a regular interval. You have to just avoid the conditions, so that there is no crevice gap, there is no crevice zone in the metal. So, you have to be very much careful to avoid silting, and also if you just flow the air properly or flow the water properly, so that that region is properly protected, then there is less probability of crevice attack. You can also get rid of the crevice corrosion by proper choice of material. As I mentioned you, the kind of film which forms on the surface, if protects the surface to a large extent, then it can minimize the tendency of the crevice attack. For example, the case of mild steel as well as stainless steel, 304 stainless steel and 316 stainless steel. If you just compare these three cases, you will find that the minimum crevice attack will be there in 316 stainless steel as compared to that of that mild steel or 304 stainless steel, because there is stable oxide formation which is highly stable, even though there is differential aeration cell formation, it basically does not get deteriorated. Even if there is chloride in the environment, it does not, that chloride cannot breach away the oxide layer which is forming on the surface. You can reduce the possibility of crevice attack by reducing the temperature, by reducing the chloride level in the environment, by the application of inhibitors in the environment, and also by cathodic protection. So, these are the different ways by which you can reduce the probability of the crevice corrosion, and finally, you have to choose the proper material, so that you can get rid of this kind of corrosion to a large extent. Thank you very much.